Alright, so the next cycle that we are going to look at is air standard Brayton cycle, and this is used in turbine power plants. So the idea here is again that you have four components basically. There's four steps: 1 to 2, which is the isentropic compression of air; 2 to 3 is where the heat is being transferred to the system; then 3 to 4 is isentropic expansion, which is turbine where the power is generated; and then 4 to 1 is the heat transfer or heat rejection. Now in this case, what we do is, instead of having this heat exchanger, basically this exhaust is thrown out into the outer atmosphere, and then this compressor picks up the air from the atmosphere. So we are assuming that the air which comes out this side gets equilibrated in the outside atmosphere and then picked up by the compressor at the normal room temperature. So we don't really have this exchanger, it's just the atmosphere which picks up the heat. So let's do the same kind of analysis that we did for the previous two cycles, like Otto cycle and diesel cycle. So if you draw this on a PV diagram, then you notice that, of course, 1 to 2, which was the compressor, is an isentropic. Similarly, 3 to 4, which is a turbine, is isentropic. But 2 to 3, which was the heat supplied by the system, so that's again being done at a constant pressure, so 2 to 3. And then 4 to 1, since you rejected the heat in the outside atmosphere and then picked up the substance or the material, air, from the atmosphere, so we assume that from 4 to 1, the pressure remains constant, which would be the normal atmospheric pressure. So in this case, we have two isentropic process and two constant pressure process. So again, it's slightly different than the Otto cycle or the diesel cycle. So again, for isentropic processes, which are process 1, 2, and 3 and 4, we have no heat transfer because they are also adiabatic, so Q would be 0. And in this case, we'll have a controlled volume because air is being taken from the atmosphere and then being rejected back. And then each of these components are controlled volume components. So that means the work done in the turbine would be change in enthalpy. Similarly, work supplied to the system in the compressor would be again change in enthalpy. And the heat transfer, Q in, which is heat transfer during this process 2-3, is change in enthalpy, and heat out, which is from 4 to 1, that's also equal to change in enthalpy. So all you do is take the original full-blown controlled volume energy balance, and then when you neglect all the terms, again remember we are working at a steady state, then all terms cancel out except these terms here and then these terms here. So the net work done, of course, during the cycle would be work done by the turbine, which would be positive, and work done by the compressor, which would be negative. So since we are just using the positive sign there, we put the negative sign here. And the thermal efficiency would be just W cycle divided by Q in. So if you write this, this gives you this form. And we also define what is known as back work ratio. That means, remember, we are getting some work done from the turbine, which will be the work output, useful work output. But then we also need to put in some work back into the system for compressor. So what is the ratio of the work that is being sort of, you have to put in back for per unit of work that is being, useful work that is being done, and that's that ratio, which is WC or WT. And that would be just the change in enthalpy for the compressor divided by change in enthalpy for the turbine. And the back work ratio, basically you can see the lower the back work ratio, the better it is, because you are putting less amount of work to get more out of it, more useful work from the turbine. And so for gas turbines, it's about 40 to 80%. That means it's very high. You're pretty much putting, let's say maybe if it's a 50%, then you're putting, for every horsepower that you're putting in, you get 2 horsepower out from turbine. So it is giving you more, but still not that efficient if you compare it with the vapor power plant, which uses steam, where the back work ratio is 1 to 2%, which means for, let's say, 1 horsepower that you put in, you're getting 100 horsepower out. Or for 2 horsepower that you put in, you get 100 horsepower out. So the ratio, this back work ratio would be much smaller. That means you need to put in a lot less to get a lot more out. And that's why steam is a more commonly used working fluid, because it gives you better efficiency. So again, we can use these tables which are given for the air as an ideal gas, because again the idea is many times is the ratios of the pressure may be given, let's say pressure here versus pressure there, rather than the actual pressure themselves. And so in that case we can use these tables, which again tells us that the ratio of the pressure would be the same ratio of the reduced pressure, or sorry, relative pressure. And remember, relative pressure is not the same as the reduced pressure. Reduced pressure was defined pressure divided by the critical pressure, whereas the reduced pressure was defined in chapter 6, which is slightly different term. So if we go back and do this analysis, and remember for adiabatic process between 1 and 2 and 3 and 4, we can use the relationship that we developed for the polytropic process, which are also adiabatic for ideal gas. And that gives us T2 over T1 as P2 over P1 to the power this K minus 1 over K. So we can develop some relationships, and based on those relationships, and I'm not giving you the details here, go back here, and for cold air standard cycle, again the change in enthalpy would be just Cp times change in temperature, where Cp would remain constant. That's what the whole idea of cold air standard analysis is, that this ratio of the heat capacities or the heat capacities themselves remain constant. So that means we can replace change in enthalpy by Cp times change in temperature. So Cp of course cancel out, and you can simplify a little bit and then use this relationship which says T2 over T1 is T3 over T4, and eventually we get a relationship which says N is 1 minus T1 over T2, and then you can rewrite this in terms of the pressure, ratio of the pressures and the K value. So if you plot this compression ratio versus efficiency, you get something like this. So that as the compressor pressure ratio increases, which is P2 over P1, so as this ratio increases, the efficiency increases. So keep in mind the quantities which are given in table A22, PR and VR, they are relative pressure and relative volume. They are distinct from the reduced pressure and the reduced volume that we defined in chapter 3.